All right, so we were partway through question number 3 on the 2006 final. I sent Jim copies of the 2006 and the 2005 final to College of the Rockies, so he should post those to the Moodle site for you, if he hasn't already. And you guys have access to the finals and to past answer keys on our Blackboard site.
So there's another review I didn't have, not just the 2006.
I think there was already 2 there.
Oh.
All right. So in this question, just to recall, we were looking at the bucket of the bulldozer, trying to figure out the horizontal force required in cylinder JC, the force in cylinder EI, and the force in cylinder BF. And we started with the bucket because it had the least number of forces on it. And we found the pin force at G, and we found EI. We found part B for the question. So what should we do next? We still need to find this force and this force. There's more than one right answer.
Draw the DFG and find the force.
Right. So if we keep working our way to the left, we can do a free body diagram of the beam DEFG. And the only unknowns on it now are the 2-force member, which is the cylinder BF, and then the pin forces at D. So there's 3 unknowns, which is exactly the number that we can solve for with our equations of equilibrium. So that's what I would do. We also could do a free body diagram of the whole thing to figure out what this force P is, because if we do the whole assembly, then the only external forces are the pin at A and this link JC. Everything else becomes an internal force. But since we've already broken it down to do the bucket first, I'd continue to work in pieces. So let's take a picture of that section. That's a blank page right there. So that's DEFG. So we've got a little bit of extraneous material on here, but what forces do we have acting on DEFG? What forces do we have on D? Right, there's going to be a reaction force which could be in any direction, so we'll break it down into X and Y components. Don't know the direction, so I'm just going to assume that it's positive. G, dy, and dx. What else?
Assume a tension force in the cylinder.
Okay, FB, you want to assume tension? I think it's going to be compression too, but it really doesn't matter. We can assume whatever we want. If we assume tension and it's compression, it's going to come out negative. So let's assume we don't know. We can't figure it out, so we would draw it in as tension. Call that one F. That was BF, right? BF. And EI, we already found. And EI was in tension. And it was 2.89 kilonewtons. I can scroll back and check. 2.887 kilonewtons. 2.887 kilonewtons. What else? Pardon? Right, the reactions at G. But the reactions at G on this part are going to be opposite to the reactions of G on this part. So here we had a positive X and a positive Y. So on section D, E, F, G, it's going to be a negative X and a negative Y. Same magnitude, it's the reaction force. So we can draw the GX this way and GY this way. I don't know how to get that. 2.887 kilonewtons. There, fits. Anything else? Nope, that's it. So we've got 3 known forces and 3 unknown forces. So we would go then from the free body diagram to the equations of equilibrium. One of our equations of equilibrium is going to have to be a moment equation. What point should we take the moment about? D. That gets rid of 2 of our unknowns, so we can then solve for FBF, which is really the one we're looking for. Sum of the moments about D equals 0. But before we go any farther, though, we're going to have to figure out this angle. And to figure out that angle, I'm going to have to look at the big picture for a second. All right, so how can I figure out this angle? We're going to have to use the cosine law. Because I know this length, and I know this length. Oh, can I use the cosine law? Because I don't know this length. Pardon? No, we should be able to. So that's what I did before. How to figure out. Oh, I used the cosine law to figure out this length. But I did it using a different triangle. And then I used the law of sines. Actually, I should be able to do it. I have side, angle, side for this triangle. So yeah, I can use the law of cosines to figure out the side length. So if we call this side length L. This angle is 60 degrees. So L, by the law of cosines, does anybody remember the law of cosines? Right, so in this case, this is our C, so L squared is going to be 1.8 squared plus 1.2 squared. Right, this side's 1.8, this side's 1.2. And then minus 2, 1.8, 1.2 cosine of the angle between, which is 60 degrees. So L is going to be the square root of that. .587 meters. And then once we have L, then we can find this angle theta by the law of sines. Right, so that's going to be sine theta over the opposite side. The opposite side is 1.8 equals sine 60 over the opposite side, which is L, which is 1.587. And if we solve that, we should get theta. Okay, 79.11 degrees. That seems about right. I'll zoom back out. And that's 79.11 degrees. So now we can look at the moments about D. I have FEI, so that can be a positive or negative moment about D. That would be positive the way it's shown, so it's going to be a counterclockwise torque or moment. So the distance is 0.6. The force is 2.887. And the angle between this angle is the same as, well, it's going to be 60. Right, because this is 30 from vertical. So that'd be sine 60. Next force that's going to produce a moment is going to be this one, FBF. That's going to be positive or negative moment? Negative. So minus its lever arm, 1.2 meters. FBF. Sine 79.11 degrees. And now we've got FGX and FGY, which are both going to produce moments. If we look at FGX, is that going to be a positive or a negative moment? That one's also going to be negative, so negative 1.8 meters, 2.887 kilonewtons, and the angle between is 60 again. And then FGY, positive or negative moment? Negative. The angle between it's going to be 30 from this angle. Well, we go 60 plus 90 if you want, which would be 120. But sine 120 is going to be the same as, sorry, 60 plus 90 is 150. Sine 150 is the same as sine 30. But we can put in the 150 if you want. All right. So, oh yeah, sine. So there's only one unknown in there, so we should be able to solve that. It's definitely going to be negative. Let's wait for at least one other.
What did we get? Yeah, I got that.
What did you get, Mike?
10.1.
Negative 10.64 kilonewtons. So that tells us it's not in tension, it's in compression, which if we stared at it, we probably could have figured that out. All right, so we still need to find this force. So what are we going to do now? Actually, we're not quite finished the equations of equilibrium here. We haven't found the reactions at D. Once we find the reactions at D, then I can do a free body diagram of the last section to find the missing force.
Or could we do the whole thing?
We could do the whole thing, yeah. We could, yeah. Would you rather do it that way? Okay. Since we're only looking for those forces, that would be an option. If we needed to find all of the pin forces, then we'd be better just to keep going. Okay, so the entire assembly is going to be a little bit messy. Just because I already have all that markup in there. What forces are acting on the entire assembly?
The weights.
Right, I've got 3 weights. I've got the weight of the bucket, which was 10 kilonewtons. I've got the weight of this section, which acted at E, I think it was. But we forgot to put that force in our... shoot. Forgot to put that force in our last. That's why the answer is a little different than what I have. So that was 1 kilonewton. And then we have the weight of the last part, which is acting at B. And it was 2 kilonewtons. All right, let's go back and fix the last section. So we needed to also add a force in here. I'll draw it this way. And that was the weight, which was 1 kilonewton. Which is going to add another term to our moment equation. Is that a positive or a negative moment? Negative, it's going to be clockwise. So that's going to be 1.2 meters, 1 kilonewton, sine, what's the angle there? Well, if we measure it from here, it'd be 30, or if we measure it from this side, it'd be the same as this one, it'd be the 150 degrees, but it's the same thing. And then we recalculate FBF, and it's still going to be negative 10 point something. Okay, 10.69. What did we have before? 10.64? Yeah, so it wasn't a huge difference because it's not that much weight. Negative 10.69 kilonewtons. All right. Pardon? Oh, yes, it is 0.6. Yep. Put it in the wrong place, too. 0.6. Yep. That probably changes it again.
I got 10.44.
All right, that's what I have from before. 10.44 kilonewtons. Still in compression. All right. Back to our free body diagram of the entire assembly. What other forces are going to be active? Force P, yeah. What else? Reactions at A. That's it. So that'd be AY and AX. What next? Equations of equilibrium. Start with, actually we only need one of them, moments about A. So if we work our way to the right from A, first thing we get to is B. So I could figure out that horizontal distance, or I could just figure out, the angle between the 0.9 meter distance and the force, which is probably going to be easier. So that's going to be 0.9 meters times 2 kilonewtons times sine 30. And that's a negative moment. And then we get to P, which is going to be a positive moment. So plus 1.8 meters. Times P times sine 60. All right, now we're going to get a little bit trickier. Because now I can't just take the angle between, I'm going to have to figure out these lengths. Is that going to be positive or a negative moment for this next one? Negative. So that's going to be minus. And this length, or the horizontal distance, is going to be these three. So 2.7 sine 30. And then we got plus another 0.6 sine 30. All times 1 kilonewton. And then the last one, I'm going to have, again, minus, this is 2.7 sine 30. This is going to be 1.8 sine 30. And then plus this 0.3 at the end. And that all has to be multiplied by, I'm just going to move that over just a bit. Or 10 kilonewtons. A 17.98. Yeah. 99. 17.99 kilonewtons. So if I was doing this on an exam, I wouldn't go straight from here to here. I'd kind of rearrange all the terms, show how I'm calculating it, so that if I make a mistake on my calculator, there's more there to give part marks for. So you can show that it was just your calculator that made the mistake. Wow. Just you putting the numbers into the calculator. All right. For those of you in Courtney, there will be a shear and moment diagram question on your exam. College of the Rockies, I assume there will also be one for you, but I'm not sure because I haven't seen your exam. So for this one, we want to draw the shear and bending moment diagrams. It says to ignore the overhangs past the roller and the pin. Be sure to indicate the values and slopes of the plots at all necessary points. How would we start this?
Finding the reaction forces of the usual.
Okay. There's not really room underneath, so I'm going to do this on the top. Okay, so the reaction forces, they haven't labeled the points, so let's label them ourselves. Let's call this one A. We can call this B, C, and D. Actually, probably should have labeled that one as well. So let's go C, D, and E. So where are the reactions going to be? A and B. A and E. That's what I meant. What's the reaction at E going to look like? E can only be a vertical force because there's a roller on a horizontal surface. We'll call that one EY. What about at A? A is pinned, so there could be an X and a Y. I'm going to draw the X1 dash though, because by inspection we can tell that it has to be 0. There's no horizontal forces on the beam. All right, so how are we going to find those two remaining reaction forces? Equations of equilibrium. Specifically, right, so we'll start with a moment equation. I could do moments about A, or I could do moments about E. I find it easier to work from the left over, so I think I would choose A, but it doesn't really matter. All right, what's the first thing that I have here? Okay, moving from left to right, the first thing I have is the distributed load. So the distributed load is 8 kilonewtons per meter, uniformly distributed over 4 meters. So the equivalent force for that would be 32 kilonewtons, and it's going to be at 2 meters from the end. And it's going to be negative, right? Negative moment. That was 8 times 4 is 32. Next thing we have is this 5 kilonewtons, also producing a negative moment. So minus, and that's also at 2 meters. 2 meters, 5 kilonewtons. And then at point B, we also have this couple moment. Positive or negative? Negative. It's clockwise, so that's going to be minus 5 kilonewton meters. Okay, I keep moving. I get to C, that finishes the distributed load we've already accounted for. Now I get to D. D has a force and a couple moment. So if I look at the force first, positive or negative moment? Negative. 2, 4, 6 meters times 5 kilonewtons. Couple moment, positive. So that's plus 5 kilonewton meters. And then I finally get to E, positive moment, 8 meters times EY. Exactly? Yep. Okay, so 13.0 kilonewtons. Okay, and then we would find AY by using the sum of the forces in the y direction, or we could do moments again. If we use forces in the y direction, we have AY minus 32 minus 5 minus 5 plus 13. From that, we should get AY. I get 29. Yeah. All right. That's actually all of the calculations we need to do to produce the shear and moment diagrams. What's the shear diagram going to look like on the left? Well, it starts at 0, and then it immediately jumps up from the force at A to 29. So let's use blue for our shear diagram. So it jumps up to 29. Then what's going to happen? It's going to go down with a slope of -8 for 2. So how far is it going to go down? 16 from 29 is 13. So a little less than half. Then what happens at B? It drops down by 5. And then what happens? Oh, sorry, it's dropped down by 5. So what's the value now? 8. Okay. So it continues with a slope of -8 for 2 meters. What's the value now? -8. Okay, and then what happens between C and D? Nothing, right? Just a horizontal line. Continues at -8. What happens at D? Right, drops down by 5. Which means it's now -13. What happens between between D and E? Horizontal line. And then at E, it's plus 13 for E for the reaction force EY. So let's write in those numbers we were saying. So this is 29. This is slope of -8. And this is 3 kilonewtons. That's kilonewtons per meter. So this value was 13. This value was 8. This value was -8. This value was -13. This slope was -8. All the other slopes were 0. So that's actually really easy if you've got the loading on the top to produce the shear diagram. It's almost as easy to produce the moment diagram once you've got the shear diagram above, and these couple moments that we have to consider as well. So if we go to the moment diagram, oops. And we'll use red for that one. How are we going to produce the moment diagram from the shear diagram? It's the area under it. That's right. So between A and B, we're basically just looking at the area of the trapezoid, of the increasingly descending trapezoid. What's the shape going to look like? Right, it's going to be a parabolic shape or a quadratic graph of a quadratic equation. It starts at 0 because there's no couple moment at A. So the area here starts at 0, and it's going to be increasing the whole time, but it's increasing at a decreasing rate. Or its slope is decreasing. So that would be something that looks maybe like that. Okay? What's this value going to be? This is 0. The value here has to be the area of this diagram. How do you figure out the area of a trapezoid? Right, so we can take the average of these two sides and then multiply by the distance between. Or I could turn it into a rectangle and a triangle. Give me the same result. What's the average of 13 and 29? What's 21 times 2? 42. That's the value here. All right, and there's two things that happen at B. There's a couple moment. What's the couple moment going to do? Is it going to drop or is it going to go up? It is a negative moment, but is this negative moment causing a negative bending moment or a positive bending moment? The reaction moment. If we take a cut here and a cut here, and we figure out our bending moment at both of them, the bending moment's actually going to be increased on this side by this negative moment. So it's going to go up by 5. So we have a jump up by 5. So it goes from 42 to 47. What about this drop? What does that do? Well, it does do something. It changes the slope. So the slope here is 13, and the slope here is only going to be 8. Okay, so what's it going to look like between B and C here? That's going to be a top of a parabola. So that means we're going to, by symmetry, it should end here on the same value of 47. And this 0 is going to represent my maximum. How am I going to figure out what that maximum is? It's not difficult. It requires no calculus.
Base times height.
Right, we're going to add the area of this rectangle is going to be how much this goes up between here and here. So half base times height, the base is 1, so it's half of the 2 meters. So it's the area is 4. So we go from 47 up by 4 to 51 kilonewton meters. Then we come back down to 47. What's going to happen between C and D? Right, it's going to be a straight line with a slope of -8 for 2 meters. So if it's a straight line with a slope of -8 for 2 meters, starting at 47, what value is it going to go down to? 31. So something kind of like that. And this value is 31. What's going to happen at that point? What two things are going to happen at that point? It's going to drop because of the couple moment by 5. And the slope is going to decrease by 5 to -13. So we're going to have a drop. 31 minus 5 should be 26. And then the slope's going to increase. Well, it's going to become more negative. This isn't exactly to scale, but it's not bad, and I'm going to label the slope anyway. Slope equals -13. And a slope of -13 from 26 brings us back to 0, and that's our check. If there's no fixed support, the moment diagram needs to start and stop at 0. There. We did the whole moment, shear and moment diagram without doing any calculus. You also could have done, and if you had time on the exam, do a check. Somewhere in each section, draw a cut line and figure out the shear and moment as a function of x. It's going to take you more time. This method's much more efficient. But if you have time to do a check, then do the calculus method. Actually, it's the equilibrium method. All right, any questions on the shear and moment diagrams? You should practice some of those before the exam for sure. All right, this next question. Has a beam that has a mass of 20 kilograms and is subject to a force of 150 newtons. That's this force here. Yep. Okay, let me see if I can toggle it back. Otherwise, might want to reconnect it. It's already on. Got it back? I think that was an affirmative. All right, so it's supported by a pin at A and by a 4 kilogram spool at B. The minimum cable force P required, or we're asked to determine the minimum cable force P required to roll the spool out from under the beam, and the direction the spool rolls, to the right or to the left. And we're given coefficients of friction at B and at D. So B is at the inside of the spool where the beam is supported by it, and D is where the spool contacts basically the ground here, horizontal surface. Where do you think it's going to move? It could go to the right, it could go to the left. How are we going to figure it out? We're going to have to guess impending motion in one direction, and hopefully we guess right, but if we don't, then we'll know, and we'll solve it guessing the other way. So what would your first guess be? So your guess is impending motion at D? If we have impending motion at D, then it's going to move to the left. That's right. All right, so how are we going to confirm that? It's the first thing we need to do. We're going to do a free body diagram of the spool. But we are going to need a free body diagram of the spool. But I think if we do a free body diagram of the beam first, then that will tell us what the force is on the spool. So let's start with the beam. And the free body diagram of the beam is going to be the same either way. Well, no, the friction force would be different depending on which one slips. So if we draw the beam first. Nope. Just the friction parts. All the calculations will have to be redone, but the equations that you've set up will mostly be the same. So if this is the free body diagram of the beam, and this is A, and this is the 150 Newton force, and then this is B. What forces do I need to add? Okay, so the normal force from the spool on the beam, so we can call that By. Reaction forces at A, so that'd be AX and AY. And the friction force at B. Yeah, we should probably call that NB, since we're dealing with friction here. NB. What direction is the friction force at B going to be? On the beam. On the beam. If I pull the spool this way, it's going to be pulling the beam to the right. So the friction force would be to the right, which means my reaction force is going to be in the opposite direction. That's okay. We'll fix that. That'll resolve itself. So we've got F, B, and sorry, we have one more. The weight of the beam. The weight of the beam happens to act at exactly the same point as the 150 newtons. Okay. There's my free body diagram of the beam. What are we going to use for our equations of equilibrium to solve? But I actually have 4 unknowns. I'm not going to be able to solve it. Totally. So I can do moments about A. That actually gets rid of all of the unknowns except for one. Because AX and FB both go through, have lines of action through A. So I have one positive moment, which would be NB, which would be 4 meters. 4 meters. NB. Because I've got 2 meters. Oh, sorry, 3 meters. Right. Yep. 3 meters NB minus 2 meters, 196.2 newtons plus 150 newtons. So I should be able to calculate NB from that.
230.8.
That's what I've got, 230.8 newtons. And I could figure out AX and AY, but I don't really need those because really we're dealing with the spool here. So we'll go on from that to the free body diagram of the spool. So my spool is going to be 2 concentric circles. All right, what forces are going to be acting on the spool? Pardon? The pulling force P, yep, so I can write that one in there. That's on the top. Normal force, the one we just calculated, so we got a normal force which is going to be down on B. Friction force to the left. NB I know is 230.8 newtons. Normal force on the bottom. So that's going to be ND. Okay, which direction is the friction force? It's going to be to the right. Yeah. It's to the right. Think of a bicycle wheel, right? So if you put a moment on the bicycle wheel or a torque, it pushes the ground back, but the reaction force on the wheel, it's going to be forwards. So that's going to be Fd, and we assumed impending motion. So Fd is going to be the coefficient at d, which is 0.1 times nd. Okay, what else? It did have a weight. Well, it had a mass. 4 kilogram spool. So we can write its weight in. All right. What next?
Find any or equate equilibrium.
Yep.
Like the y direction first, and then moments about it.
Yep. So I'll start with Fy equals 0. So I got Nd is up. I got 39.24 down. And 230.8 that's down. Okay, I'm just going to go 270.0. So Nd equals 270.0, which means Fd equals 27. If we have impending motion at d. Now we can go to the moment equation. What are we going to take moments about? We could take moments about center. Problem with taking moments about center is I'd have two unknowns. Or I could take moments about a different. Right, so we could take moments about B. Right, so this is B, this is B. So we do moments about B, then I'm only going to have these two forces. The radii that are given, I should put those on the diagram, 0.1 and 0.3. So this is 0.1 meters and this is 0.3 meters. So if we're looking at moments about B, Fd is going to be a positive moment. What's its lever arm going to be? 0.4 meters, right? So it's going to be 0.4 meters times 27 newtons. And then that's going to be a negative moment, and its lever arm is going to be 0.2 meters. Times P. Your calculator's clicking, but you shouldn't need a calculator for this. 54. 54 newtons, twice the 27. What's left? That's all we were asked for, right? Was P? we're asked for P in the direction the spool rolls. We assumed that it's going to roll to the left. Now we need to do a check. How are we going to check? Right. Based on our assumption, we can now figure out what this friction force is. And if this friction force is less than the coefficient times NB, then we guessed correct. If this friction force is greater, then I'm going to have to recalculate assuming impending motion at B instead of D. So, find FB from equilibrium. Okay, so that would be sum of the forces in the x direction equals 0. It's our last equation. Forces in the x, I've got 27. I've got 54. And then I've got in the negative direction, I've got F sub B. So now we have to ask ourselves, is 81 newtons less than or equal to, what was the coefficient? B 0.4 times NB, which was 270. And the answer is yes. So fortunately we guessed correctly. Okay, if you don't guess correctly, it's not a big deal. You just go back and you switch which friction equation you're using and which one you're going to solve by equilibrium in it. Yes, you're redoing all of the calculations, but the free body diagrams and the equations of equilibrium aren't actually all that different. You're just punching the numbers into your calculator differently. All right, I think we've got one more question. And this is a truss question. Those of you writing here and in Campbell River, I love trusses. I love truss questions. So you should probably be ready for one of those. So there's a problem in the book like this one?
Yeah, like that exact diagram.
Okay. So this one is something called a Warren truss. And a Warren truss, I don't know if that's Y, but a Warren truss has W's, right? So they're going to be equally, none of the webbing are going to be normal to the top and bottom chord. They're always at the same angles. This Warren truss is used to support a staircase. So it's got different loads at each one of the nodes on the top chord. Assuming that all joints are pinned, calculate the magnitudes of the internal forces inside members CD, DE, and DF. So CD, DE, and DF. There is more than one way to solve this. How would you like to solve it? Right, so the suggestion was to do the method of sections, and you certainly can do method of sections. We're looking for CD, DE, and DF. So let's just highlight those ones. CD, DE, DF. So oh, sorry, DF. I can't do a single section cut through all three of those, but I can do a single section cut to solve for two of them, and then just use the method of joints to find the other one based on the other two. Like I cut a section through here, and then when I'm finished finding these three by the method of sections, then I'd use method of joints on D, and there's only two missing forces there. That would be one method. A longer method would be just to use the method of joints, go from A to B to C to D. So 4 free body diagrams of the joints. Actually isn't that bad because the joints go quickly. There's no moment equations. That would be acceptable as well. We could also start at the other end. We can do left sections or we could do right sections. If we're going to do the method of sections, which I would recommend for this problem, we need to find the reaction points first, or the reaction forces first. All right, what's the nature of the reaction forces at A and at I? Right, so A is going to have a Y and an X. And B is, it's a pinned joint, but the pinned part here is now on rollers, so it can only be normal to the surface of contact. So it's going to only have an X. And it can only be to the left. So the rollers aren't going to hold it in. So there's my free body diagram. I actually only should need, no, I need 2 equations of equilibrium. Which one do you want to do first? Okay, so we can do moments about A to find IX, which is going to have to be equal and opposite AX. And then the other one is going to be the forces in the Y direction. All right, so if we move out from A, first thing we get to is this 800 Newton force. That 800 Newton force is going to cause a negative moment, and the lever arm is 2 meters. At 4 meters, we have 1500 newtons. And then at 6 meters, we have 800 newtons. And then at 8 meters, we have 400 newtons. And then we have our one positive moment plus Ix at 2, 4, 6, 8 up, not 8 over. So plus 8 meters Ix. For some reason I don't have a solution for this one. I'll wait for one other. 1,950 newtons. That also has to equal AX. Okay, and then we're going to do forces about the Y. Actually, I don't have to do forces about the Y if I'm going to do a right section. Let's do a right section. So if we do our section cut, through here, then my free body diagram oops. Then my free body diagram looks like this. And it's going to have force here, force here, force here, all assumed to be in tension. Ix was already found to be 1950. Oop, looks like we're out of time. 1950 newtons. It's going to be FDF, FDE, and FCE. So I'll complete the solution to this one and post it. We're almost there. We do equations of equilibrium of this section to find these three forces, and then we're going to have to do an equilibrium equation at the joint at D to find the one other force that we're asked for. We're going to have to solve for two forces, but only one of them that we're asked for. So I'll finish those up before I post the notes for today.
Could you go back to number 4?
Yep, just a second.